Hello.
Yes.
Yeah. So, welcome to our second half of our today's research summit session. Uh, yes, Dr. Mohammed Ashefas, you can share your screen and you are now audible. Yes. Yes.
Okay.
Okay. Yes.
Thank you.
So, let me introduce him formally first. So, Dr. Mohammed Ashefas is assistant professor of government Brennan College. His interest is in quantum optics, and today's title of his talk is Kerr-Nonlinearity enhanced single photon blockade in Jaynes-Cummings model. So I am handing over the stage to you. Ashefas, you can start now.
Okay. So thanks for the nice introduction. So, this work, this Kerr-Nonlinearity enhanced single photon blockade, I have done during my PhD work. So I would like to introduce my guide and as well as my collaborator. So Dr. Ramesh Babu is my guide, and Manoj is my collaborator for during this work. And this work is published in International Journal of Theoretical Physics. And before going to start this presentation, I would also like to thank the organizers of QIQT for giving me such an opportunity. So we know that this QIQT is one of the biggest conference happening in quantum information and quantum technology. So I am very happy and very glad, and as well as I am very honored of getting this opportunity for presenting this work. So we can start with our presentation. So this is the total outline of this presentation. So I'll give a brief introduction, then introduce what is photon Blockade effect, and then we'll go to the photon Blockade effect in JCM and the motivation of this present work. And as well as we'll thereafter we'll introduce the major work, which is the photon Blockade effect in driven dissipative Jaynes-Cummings model with Kerr medium. And as well as we introduce a new measure to verify the presence of photon Blockade effect, which is our proposal. And finally, we will have a conclusion. So the generation manipulation of single photon are one of the important goals of quantum optics. So it reveals the non-classical nature of light and has application in quantum technologies in like quantum computation, quantum information, quantum metrology, etc. So one of the possible way to produce the single photon blockade, this single photon, is by the photon blockade effect. So it can be achieved in various systems, including the Jaynes-Cummings systems. It can be achieved in single cavity also without atom, and it can be achieved in Jaynes-Cummings system as well. So it is a phenomena of the single photon blockade is a phenomena of restricting the number of photon equal to 1. And it blocks the additional photon, the presence of additional photon. So technically, in technical terms, we can call it as an anti-merging phenomena of higher number of photons. A system which satisfies the single photon blockade can be used or can be treated as a single photon source. So this is the main idea behind our work. So if you can achieve a single photon blockade in a system, it can be used as a single photon source. So how to verify the presence of the photon blockade? So the verification of photon blockade is possible by two measures. So mainly the probability of number of photons denoted by symbol capital Pn, and the correlation function, the nth order correlation functions denoted by symbol Gn, and as well as we have to know the Poissonian distribution. It's a photon probability distribution of coherent state, and it is denoted by symbol script Pn. So we have two criteria. The first criteria is based on the probability. So the probability of a single photon in the system must be greater than the Poissonian probability corresponding to single photon. And as well as the probability for higher number of photon must be less than the Poisson distribution. The probability corresponding to the higher number of photons of the Poissonian distribution or the coherent state. So it's the first criteria. And the second criteria is that visible. The second criteria. The second criteria is based on the correlation function. So according to the second criteria, the second order correlation function must be less than 1, and the third order correlation must be less than the second order correlation, so on. So these are the two criteria to check the photon blockade effect. And this can be achieved in Jaynes-Cummings model. So how we can achieve the Jaynes-Cummings model, that I will explain in this slide. So we already know about the Jaynes-Cummings model. It is a two-level system, is confined in a cavity, a single mode cavity. So the Hamiltonian of Jaynes-Cummings system can be written in this way: this omega r a dagger a plus omega 0 sigma plus sigma minus, and then g a sigma plus a dagger sigma minus. So here omega r is the frequency of cavity, and omega 0 is the transition frequency of atom, and g is the interaction strength between the atom and field. So in this entire thing, we have put this cross equal to 1. So the energy level diagram of the system can be shown here. So in the left side shows the energy levels of the bare states. So bare states are represented by the symbol for the ground state. The bare state is G0. So G represents the atom in the ground state and 0 photon. Then first excited state is represented as get G1, the atom in the ground state and just having single photon, or the atom in excited state and no photon present. So both G1 and E0 can be called as the single excitation state. Okay. Now in this diagram, I have assumed this omega r and omega 0 are same. Omega r and omega 0 equal to omega. So that is I have mentioned here. Then the second excited state, the states are G2 and E1. So these are the base states, and we can see here that these base states are not the eigenstates of the Hamiltonian, the Jaynes-Cummings Hamiltonian. So the eigenstates of the Jaynes-Cummings Hamiltonian will be the superposition of these bare states. So for single excitation, the energy eigenstates would be the superposition of G1 and E0. And the second excited state, the corresponding second excited state will have the superposition of G2 and E1, so on. So there are two possibilities of superposition. So one superposition gives the energy omega minus G, and the second superposition gives energy omega plus G. So what happens is for the energy eigenstate, there is a separation between the energy level, even for the single excitation, and the two excitation. There is again a separation, and the separation increases with G. So you can see here the separation. The first separation is G, and second separation is √2G. The third separation is √3G, so on. So these separation energy levels we call enharmonicity, and this enharmonicity helps the Jaynes-Cummings system to achieve the single photon blockade effect. So this can easily we can explain it here. So suppose if you have some external driving, and if you want to excite the system from the ground state to the first excited state, so that I can show here. So if you excite the system from ground to the first excited state, then using the same frequency, you could not be able to excite the system to the second excited state. Second excited state means with two excitation. So this kind of enharmonicity helps us preventing the further excitation of the system to the higher energy levels or to the higher number of excitations with the single frequency. Whereas in case of uncoupled state, if you send the frequency omega, it can go in ladder. It can go to the first excited state, then go to second excited, and so on. But due to the enharmonicity in the Jaynes-Cummings system, it is not possible. It cannot go to the higher energy state. Okay, so this is the basic physics behind this. Okay, but still the energies are exactly not matching, but there is some probability to get the system to excite the system to higher energy levels. So that is one issue. Is if G is very small, what happens is there is a possibility of higher excitation even with the same omega. It is if you excite to the first excited state, it can go to the higher excited state if G is very small. So if G is large, then we can limit the excitation to the single excitation subspace. So the single excitation means the number of photons would be equal to 1. Then, so this condition usually called the photon blockade. So we restrict the maximum number of photon. If you can restrict the maximum number of photon in the system is 1, then we call it the single photon blockade. Now, in the Jaynes-Cummings model, now the issue is we should have a reasonable G to get the single photon blockade effect. So that means we require the strong coupling. So the strong coupling regime is important in order to get a good the photon blockade effect in the usual JCM. So there is one issue. So if you are going to the higher coupling strength, then we cannot use the rotating wave approximation that we already used here, because here we have already used the rotating wave approximation. There is a term only A sigma plus and A dagger sigma minus. So we have removed the term like A dagger sigma minus and A sigma plus. All these terms are not visible here because we already used the rotating wave approximation. So when you are going to the higher coupling strength, then we have to neglect the rotating wave approximation. That means we have to include the more terms in Jaynes-Cummings model, etc. So those issues will be there. So it is possible to remove the condition of the strong coupling regime if you can able to increase the enharmonicity of the energy level through an alternate means. So one possible way to increase the enharmonicity or increase energy levels separation is by introducing the Kerr-Nonlinearity in the Jaynes-Cummings model. So this is the motivation behind our work. So it is already possible to produce the photon blockade in Jaynes-Cummings system. But the problem is it has to be the higher coupling strength, the G must be large. Now, our proposal is if you have the Kerr-Nonlinearity in the system, then it is possible to achieve the single photon blockade effect even for the low G. So even for the weak coupling, we can achieve the photon blockade. So that is our motivation and that's our proposal. So we have designed, our system is the schematic model is shown here. So we have a cavity, a single mode cavity with the two-level atom inside, and which is inside the Kerr medium. And both cavity and field is driven by the external laser field, and that is treated as classical field. So atomic driving strength or the qubit driving strength is denoted by symbol omega d, and cavity driving strength is denoted by symbol omega p. And for this system, the energy eigen levels in the absence of the pumping, the energy eigen levels can be denoted like this. So here the energy levels are same for the E1 minus and E1 plus. That is for first excited state is same as the earlier one. The separation is simply 2G. Like here, the separation is 2G for the first two excited state, that is corresponding to the single excitation. But whereas the two excitation, the energy levels corresponding to excitation, it depends depending upon chi. So their separation increases with chi. So that is the highlight of this factor. So even if the G is 0, then there is a separation between the energy levels. That is what is shown by this dotted line. So even if you put the G equal to 0, there will be separation. Okay, so the Hamiltonian of the system, now we have the Kerr-Nonlinearity, which is written here by the Kerr-Nonlinearity strength chi. And apart from the normal JCM, we have additional driving terms. So there is the driving term corresponding to the cavity pumping, and that is denoted by symbol omega p, and corresponding frequency is small omega p. And the qubit is driven by the another laser field, and its strength and frequency are denoted by capital omega d and small omega d, etc. Now, since it is an open system, there is also possibility of dissipation. So we have to include dissipation as well. So if you include dissipation and using a unitary transformation, it is possible to write the total Hamiltonian of this form. So while writing this Hamiltonian, I have assumed this omega p and omega d are same. That is both the frequency, driving frequency of both laser fields are same, but its the strength may be different. And we have some delta r tilde and delta 0 tilde here. Here both delta r tilde and delta 0 tilde are complex, where delta r tilde is delta r minus I kappa by 2, where kappa is the dissipation rate of cavity. And delta 0 tilde is delta 0 minus I gamma by 2, where gamma is the dissipation rate of qubit. And delta r and delta 0 are detuning, which is mentioned here. Delta r is omega r minus omega p, is a detuning between the cavity field and the cavity pump. And delta 0 is a detuning between the atomic transition and the atomic pump. And here the atomic pump frequency and the cavity driving frequency are same, omega p equal to omega d. That is why I have simply written omega 0 minus omega p. Otherwise, it should be omega 0 minus omega d. Okay, so this is the total effective Hamiltonian. Now, in order to go further, we have to find the equation of motion of the system. So for that, we have to write a general state of the system first. So general state of the system can be expanded in this way. So here we have assuming we have very weak driving. That is the strength of omega p and omega d is very small compared to the dissipation, right? So then the possibility of a higher transition would be very limited. So if the driving strength is very small, the system may not go to the higher excitation subspace. So we have limited our the total state or total excitation up to the 2 excitation. So that is why we have listed out all possible states within the 2 excitation, and a general state is represented here. And we can write the equation of motion by using the stochastic Schrodinger equation. And the equation of motion or the differential equation satisfied by the all coefficients that are written here, the coupled differential equation, and we can solve it for steady state. So for steady state, we can find the C0E, C1G, and C1E, C2G, etc. It's slightly complicated, but our important thing is the C2G, the factor C2G is very important to us, because the second order correlation function is depending upon C2G, and it must be this G2, the second order correlation function must be less than 1 in order to get the single photon blockade. So G2 of 0 can be analytically calculated, and we can show that this G2 of 0 is approximately 2 C2G square by C1G square. So because we can neglect the C1G, we can neglect C1E and C2G term, because C1E and C2G term is corresponding to the 2 excitation. So 2 excitation probability is very less compared to the single excitation probability. So that approximation that I have taken here. Now the same thing can be calculated numerically as well. So in order to compare our numerical result and analytical result, we have considered a special case of only the cavity field driven. The qubit field omega d, the driving strength of qubit field I have assumed to be 0, and the cavity field omega p is assumed to be 0.01. So I have plotted the graph, the analytical graph, and as numerical graph. The numerical is represented by the red dotted line, and the analytical graph is a black dashed line, black line, the continuous line. And it is almost matching, and there is a small discrepancy in some places, because that is expected, because we have already approximated it with G2 of 0 while it's analytical calculation. Now, so the thing is, we can either use the analytical equation or we can also use the numerical calculation. So numerical. So for the next purpose, for all the next analysis, we are relying on the numerical calculations. So the thing is, we have already assumed there is 2 driving strength, omega d and omega p. The omega d is the qubit driving, and omega p is the cavity driving. Now it is possible to find the condition for C2G, in which what is the condition for the C2G making 0 can be find out by using the previous equation. This equation, we can find the condition for when the C2G becomes 0, and this can be found that there is two possible omega d. C2G can become 0, and this omega d plus or minus are the 2 possible driving strength in which G2 of 0 can be minimized. And in case of single photon blockade, the thing is the excitation frequency must be omega plus g or omega minus g. So there is 2 choice for the driving strength, omega d plus or minus, and there is 2 choice for the pump frequency, omega p plus or minus, in order to limit the value of G2 of 0 less than 1. Because if you choose these things, the G2 of 0 must be very small. So therefore, there are 4 different choices available for us. We can have omega p minus. Omega p minus means we are exciting to the lowermost, the first excite state. with driving strength omega d plus. That is one possibility. The second possibility is omega p minus and omega d minus. Then third is omega p plus, omega d minus, etc. So we have total of 4 possible driving regime, which can have a minimum G2 of 0. So we can illustrate with the first case. The first excited state omega minus is driven with omega d plus, and we have plotted G2 of 0 and G3 of 0 because we have to compare the different orders of correlation function to verify the photon Blockade effect, because G2 of 0 must be less than 1. That's the first thing. Then G3 of 0 must be less than G2 of 0, so on. So we have plotted G2 of 0, G3 of 0 in this slide, and we have also plotted G4 of 0. Now we can see here the G2 of 0 is less than 1 in this entire parameter space. For here the x-axis represent omega p and the y-axis represent g, and the color represent G2 of 0. And the color label is given here on the right side. So the maximum is 0.7, so it is less than 1. So G2 of 0 is always less than 1 within this regime. So this is for the weak driving, omega p is small, and is for different. So the G is varying from 0 to 0.2, 0 to 1. So that means it can go from weak driving to weak coupling to the strong coupling. So in this entire region, even for strong coupling regime and as well as a weak coupling regime, G2 of 0 is less than 1. And G3 of 0 is again less than G2 of 0, because if you look at the value of G3 of 0, that is very, very visible here. So it satisfies the condition of the photon blockade according to this graph. Now it has to achieve one more condition in terms of the probability, this probability of number of photons. So that is also we have plotted. So the probability P1 and the Poissonian probability script P1 are plotted here. And it shows here the probability corresponding to single photon is greater than the Poissonian distribution. And the probability corresponding to a higher number of photon P2 is less than the Poisson distribution corresponding to 2 number of photon, etc. So with these two graphs, we can conclude this system achieves the photon blockade condition in the all regimes of even the both strong and weak coupling regimes of Jaynes-Cummings model. And we can illustrate the enhancement of the photon blockade effect by comparing this graph with without the situation without the Kerr medium. So the first one is without Kerr medium, that is with chi is equal to 0. The second graph is corresponding to chi equal to 1. And we can see here in this lower region, the lower region means for G small region, this G2 of 0 is greater than 1, since red corresponding to greater than 1. So all this region, the photon blockade effect is not occur. So for small G values and higher driving strength, the G2 of 0 is greater than 1, so photon blockade is not possible in this region. Whereas with Kerr medium, the photon blockade effect is possible in this entire region. So this is what is we are called the enhancement of the photon blockade with in the presence of Kerr-Nonlinearity. Now this the verification of photon blockade with different G2 value or different the correlation function is a tedious task. So the various measures is introduced by different scientists. So one method, one way to calculate the photon blockade effect is given by n norm. So this is a definition for n norm, but the problem is this n norm, the quantitatively it is not very much useful because its limit is not very clearly written. So only it says that this n norm must be very small to get the photon blockade effect. So due to this problem, we cannot always use this n norm, and that is why we have introduced a new measure, and this new measure is represented by script Gn. And it is based on the fact that the higher order correlation function must be less than the lower order correlation function. That means G3 must be less than G2 and G4 must be less than G3 and so on. So based on this, we have defined a new expression, a new measure. So there is nothing great here. So what we have done is, so whenever if the higher order correlation function is lesser than the lower order correlation function, this denominator would be, so the numerator would be 1. So the each numerator, so the numerator is summation. So each term would be 1 if it satisfies the photon blockade condition, and the numerator would be equal to n if you have n summation, and if you divide it by n, you will get 1. So that means this new measure must be 1 to get when it exceeds the photon blockade effect. And if this new measure is not equal to 1, then the photon blockade is not possible. So this is the idea behind this new measure. And this we have checked with our previous case. So in our previous case, we get the photon blockade effect for all values of omega, p, and g. So same thing we have plotted here. So in the earlier case, we have plotted G2 of 0 and G3 of 0, the different order correlation function. So instead, we have plotted G4. And here you can clearly see that G4 is 1 in the entire omega, p, and g. So there is a one main thing. And for this entire calculation, we have to limit then number of orders of correlation function. So we have limit up to the 5th order, and we have calculated G4. If you want, we can go to the higher order correlation function as well. That may not be required, even up to the 5th order it might be enough. Okay, so with this we are showing that this G4 is enough for showing. G4 is the single measure. G4 is enough for showing the presence of single photon blockade in a system. And the same thing we have plotted for the different parameter regime. So the omega d plus and omega minus is already shown to us. And thereafter for all other 4 regimes also we have shown here. And if the chi is 0, then for the other 3 cases, the photon blockade effect was not possible. So here what happens is when the chi is non-zero, then at some parameter regime, we get G4 equal to 1. So at least in some region, we get the photon blockade effect. So all this red region shows the possibility of a single photon blockade. And it happens only due to the presence of chi. If chi is 0, so this region is not equal to 1. It will not be 1, and no possible photon blockade effect in most of the cases. So this is our work. So the main conclusion is we have studied the single photon blockade in JSCM with both cavity and qubit driven by pumping field, same frequency in the presence of Kerr medium. We calculated equal time correlation function, photon properties, check the possibility of single photon blockade, and we introduced a new measure. And we have illustrated that this measure works and it can be used as a measure of the photon blockade. And this result will be helpful for more efficient practical implementation of single photon sources with qubit cavity system. Thank you.
Thanks, Mohammed ashefas. It was really nice of talk. So our session is now open for quick question. If you have any question, you can ask to ashefas.
Thank you for your talk. My question is, when G2 O is less than 1, then does it mean that photon statistics belongs to subbosonian?
When G2 is less
than 1.
When G2 is less than 1, it is subbosonian.
Yes.
Yes.
Okay. And second question is, for what purposes you need cavity?
Cavity.
Yes.
Okay. The cavity is required for the quantum interaction between the field and the 2-level system. So usually, if you have the atom without any cavity, then different modes are possible inside. It can interact with the atom. So if you have a cavity, then it is possible to have a single mode inside the cavity which interacts with the system, and this is a simple model of the atom field interaction.
Okay, so to select some specific modes which are required to study the atom. Okay. Mhm.
Yes, sir.
It's clear. Thank you.
Is there any other question? If it is not, then we are moving to our next talk. Thanks, ashefas, for your nice talk.
So once again, thanks to you as well, the organizers. So may I pause the share?
Yes.